Integrated Landscape Hydrology Model. This is a tool that we developed at Michigan State. I developed it along with Dave and a couple other students as part of my, or as the bulk of my PhD research. And this graphic really displays what I want to do with it. What I want to do is I want to be able to put rain or snow on, and I want to tell it what temperature it is on a given day. And then I want to have it say, well, how do the forests respond? How do the water falling in lakes then get routed through rivers out into whatever, the ocean or Lake Charlotte? How does an urban area respond? How will the snowpack retain moisture? How will irrigated agriculture need water? And regular agriculture. And then when it gets down through the root zone, what's it going to do in groundwater? And this type of model is what's called an integrated model. It brings together what were typically separate domains, 4 different domains of hydrologic modeling. So, scientists like to subdivide and conquer, and they did it by simulating ever smaller parts of the world until finally they were successful at, well, we could get flows in a river right. As long as we tell it exactly what the flows are, we can get the rest of the flows right. So you've got to get all those inputs. But those people had to put a number for the groundwater value. They didn't know what the groundwater inputs were, and they just had to adjust it. And then there were the root zone people who said, well, let's simulate what's happening with plants. But once it goes out of our root zone and it goes down deeper, well, it's just kind of lost. It's a loss. The deep unsaturated zone people said, well, the roots are giving us some moisture, and then we've got these really complicated things that are happening where we're not quite to the water table yet, but water is flowing through the ground. It's a really difficult thing to model, and so there's entire research groups that have built their careers out of that. And then there's the saturated zone, the water table, what we would normally think of as a groundwater aquifer, where an intensive amount of effort has gone into and a lot of money, because this is obviously of use for water resources. So we and other groups are around the same time said, hey, we've got the computer power to do this, we've got the data we need, let's just bring these all together and let's just see what happens. Simulate it all at the same time. And we built this to do really big scale. So we're looking at the Jordan River, but I'll show you the model we're doing. This is not a small area we're looking at. But at the same time, really capture fine resolution. And what we mean by fine resolution, that's something that can differ depending on what question you're asking. But we didn't want to just do big and have to sacrifice all of the information that we could learn by looking at what's happening right here. So we wanted to sort of match those two up. I'll skip that next point. It's relevant to a different audience. And when you're working at the big scale, you can't have everything be, well, here's the data value, I'm going to copy that and I'm going to click it over into my model. That doesn't work. We need to take big sets of data that were maybe collected by a satellite, or people have put them into a computer map called a Geographic Information System, or a GIS. And we've got to be able to pull all these inputs together, and you have the computer automatically assemble them to everything be to match precisely, and so that's how we built the model. And it simulates the landscape water cycle. So not the oceans, not glaciers. And we give it precip, and it calculates evaporation from the canopy, or transpiration through its roots, evaporation from the soil, or sublimation, which is just evaporation from snow. It accumulates a snowpack, it melts, deep percolation goes down, becomes recharged in the groundwater table. So it does the whole system. And this is, it's cool, but it's not totally unique. There's other things that do this too. Yeah, I already described that for you. And of note, it uses a code called ModFlow, which was built and developed by the U.S. Geological Survey. It's used worldwide. It's the standard in groundwater modeling. In addition to what's going on in the upland areas, the dry areas, we also have a completely separate take on what happens in the wetlands. So wetlands behave differently. This portion is a little bit less relevant for the Jordan River Valley because there are very few wetlands, actually. So when we talked to you guys last year, I'm sure some of you remember us talking about our model. We had a model of the Jordan River watershed that was just expanded a little bit beyond it. And since then, for various other projects, really, we've gone and we've built a bigger model that covers about half of the sort of tip of the mitt. And we've done this in order to capture the full behavior of the Boardman River, the Charlevoix system, the chain of lakes, and then it also extends up here in these a little bit more, well, it doesn't actually get this whole system, but it gets the coastal draining features. And what we've done is, for the scale, we calculate the flows of water for every 425 meters. So 425 meters is a quarter of a mile, more or less. So each cell is about a quarter of a mile squared. And And then we run this simulation every hour for 10 years in this case. I'll show you just some of the inputs. One thing is we have to tell it, well, what does the geology look like? And in a lot of places here, over most of this area, it's covered by glacial deposits, or more recent glacial deposits that were reworked by rivers or lakes. And in some places there's outcroppings of bedrock, but mostly we're looking at fairly young sediments. And the dominant one in parts of the Jordan River watershed are glacial till, and that's a material that's just scraped along the bottom by the glacier, or maybe it's carried within the glacier. It gets scraped along the bottom and then frozen inside and then carried over 1,000 miles. And then when the glacier melts, it just kind of dumps it down. That's glacial till. Or it contains sand and gravel from glacial outwash. So this is where the outwash, the melt from the glacier, carries a whole bunch of sediment with it, and it just leaves these vast outwash plains. And this is an example here of an outwash plain, this here and this here, left by a glacier, the Mansalona Plain. We use a digital elevation model, and this is a map of elevations at each individual 10-meter point that was created from topographic maps, which I'm sure you guys have seen. And we just go from about 580 feet along the lake to 1,540 feet in the highlands over here by the Grayling Fingers. We also need soil textures. We need to know what is the soil like, because before the water ever gets into the ground, it has to go through the soil. And the first users of water are the plants. And how they use water depends very critically on the soil, so we need good soil data. Thankfully, the US government, through the USDA, has developed really detailed soil surveys. Since probably 1960, they've been working on these, maybe some of them even earlier than that. The US Soil Survey is probably one of the richest data sets on what the landscape looks like anywhere in the world. They've spent a fantastic amount of time and effort developing this, and it's something that is a basic underpinning of modern agriculture, and we're also using it. Oh, I'll just mention, just like our glacial sediments, these things are coarse. And coarse sediments means, coarse soils means water flows through them very easily. They're highly permeable or highly conductive. And that's exactly why the Jordan River has its stable behavior, because it doesn't run water off its surface. The water goes first into groundwater, and groundwater tends to smooth out the variations in precip to give you this nice, smooth, seasonal flow. We also use a number of climate and satellite inputs, so we use weather data from stations like temperature, humidity, solar radiation. And then we get precip data also from stations, but we also get it from radar, from NexRad. And then satellite data we get, one key input is something called the leaf area index. And the leaf area index just says, well, if I just look up, how many leaves do I see above me? That's essentially what it's asking. If you have a higher leaf area index, that means you are likely in a forest, so we get values around 6. And that means for every area of ground, if you took all the leaves and you put them out, you'd be able to lay them out 6 times. You'd make 6 layers stacked on top of each other. And other areas here have less. This was on August 20th, so we have values of 6 in the Jordan River, or in the state forest, and then we have values of like 1 to 2 in the agricultural areas, or in the more the rangeland, grassland type areas. So one of the basic things the model does is it predicts what the stream flow is. So here we have the Jordan River flows at the Webster gauge, and this is the gauge values reported by the USGS, and here are our model values in red. So you can see that the model, first of all, it systematically underpredicts flow. And there are a couple of reasons why we think that it's systematically underpredicting, but we're comfortable with the fact that it's being systematic about it. It's not being random. And it matches the overall seasonal behavior quite well. So what this tells us is that we've got some parameters within the model that relate to how easily the water flows through the ground at all various points that aren't quite right. So we need to calibrate the model a little bit further before we get the match that we need here at Webster. But we don't do anything funny. We don't add or subtract water. The water that Webster gets is what the stations tell us came in, or NexRad says fell as rainfall, and then the plants then use it, and they do it by all the equations that we specified. So this is a physically based prediction about stream flow, and it's something that we're really interested in because we can use it to understand going forward under, say, climate change, or going backward to when the land use was completely different. We can use our physically based model to make a fundamental prediction about how the system behaved. Whereas other types of models that have various knobs and things that you can tune and tweak, we can make this fit be really good. But that fit is based on a complex interaction between what's on the land right now, what's underneath the land surface and in the ground, and then how the stream's behaving, how people are pumping out water. And if any of those things change, then your model is an exercise in futility. So anyway, so this is our model. It's not perfect, but the things that it does well, and that is we threw it at this problem and we didn't change anything substantial in terms of how the system behaves, and it gave us an answer that was pretty close. Pretty close, obviously, you can quantify, but. So then, also, it predicts what the level of the water table is, and that's because it's an integrated model. It does both the groundwater and the surface water at the same time. And here, the model simulates groundwater levels very well. There are no significant trends along the watershed. So the way that we look at this is we say, well, here are the observed values. And these were observed when a well driller came and he drilled a residential well, or a private well, and he took a steel tape with chalk on it and found what the level it was in the well, and then he reported that to the state. One point in time at one location. So, we take this value, 1200, and then we match it over here. Okay, we've got like 1180. So we're 20 feet shy. But over the range of variability we're talking about, going from 500 all the way up to 1250, we're within a couple percent actually. And so we're pretty happy about that. And also importantly, there's no trends. So it does equally as good or poorly at the high range as it does at the low range, which means that the model is at least behaving predictably. Again, we're looking for predictability more than just like exactly matching what's happening. So now, instead of just looking at what the outputs are in terms of the flows or heads, let's look at something a little bit more abstract. Let's do something with this model that you cannot do in real life, and that's to say how much water is leaving each and every point on the landscape. And then let's look at how that varies when you change what type of land you're talking about. What if you're talking about agriculture? Okay, how much water leaves an average agricultural cell and goes down to groundwater? How much leaves an average range or open land cell? How much leaves an average urban cell? Urban here would mean East Jordan. So it's perhaps a bit different than Chicago. So this is a model, this is a synthetic experiment that could never be conducted in real life. And this is the power of the tools that we've tried to develop. We've tried to say, okay, we now have 80,000 points in our model where we can ask, what is this value of annual groundwater recharge? How much water leaves this cell and goes down to the groundwater each year? And we could never conduct an experiment like this in real life. And so it's by marrying the tools, the modeling tools, with observational data, getting confidence in our models, and then using the models to understand the system that we really feel like we've got some actual power here. So the big important thing here is when you take any of these land uses, they all basically behave the same around here, which is this is locally specific. If you went downstate, these relationships would all be different. They depend on the weather, the temperature, the soil type, the slope, everything. There's only one difference, and that's range and open land. And it's actually quite a difference. It's actually, you go from 15 inches a year up to like 19 and a half inches a year. So it's something like a 30% increase. So this is actually really significant because if we look at what happened after deforestation, where you went from mostly a deciduous coniferous-based system, where each point was recharging about 15 inches of water to groundwater each year, and you cut it down, and you burn it, or you leave it open, or you do some sort of marginal agriculture, well, it's not really going to look like modern agro-industry. What it's going to look like is range or open land. And so we went from having 15 inches a year on average under today's climate, this is a synthetic experiment, to say, well, let's just cut down the forest and see what happens. Well, we end up with 19 and a half. So that's a pretty significant difference, and it means that after deforestation, the watershed actually went through a pretty dramatic transformation in terms of how much water it could move. And the exact implications of this, I haven't quite figured out. But in the next few months, I'm really trying to put these together along with Travis's sediment transport model to understand some of the quantitative numerical impacts of this transformation. And so let's just do this experiment. So here we've got our land use today. Red is urban, yellow agriculture, green grassland, and dark green is forest. And then there's some purple shrub areas. So this is the current map. This was taken from satellites, and this is circa 2001. So it's a little bit different. There is a more modern version of this from 2006, but it wasn't ready when we prepared this last year. And if we look at the distribution for the Jordan River watershed today, we see it's about half deciduous forest. And actually there's surprisingly little coniferous, so most of the coniferous is in wetlands, so it's classified as wetlands rather than as forest. Then there's a map available that some people put together using early 1800 General Land Office surveys of what trees these people would literally, they would walk a fixed distance through the woods, and then they would look around them and they would say, well, I'm going to count the trees. And so that through doing that, they developed, at each section marker, they developed a understanding of what the ecosystem was at the time. And then, so for the entire state, we have this coverage of pre-development land cover before we got here. Well, it was mostly forested, but there were some shrub and open areas. So then we played God a little bit, and we said, all right, let's deforest this entire thing. Let's just take every forest cell and just convert it to open land. And as if we harvested every tree and we did it overnight. So that's what we did to create this deforestation scenario. So what I'm going to show you is going to take just a second to interpret. But here is a map of groundwater recharge under current land use, or 2001 land use. And the red that you see is all the water, for the most part, either water or bedrock. But you can see down to the south here, where there's quite a bit more snow and it's a little bit warmer, they get more precip. You get values of annual recharge. There's something like 70 to 80 centimeters, and in inches, that's like 30 inches a year. So they get about 30 inches a year of annual recharge down here. There's some areas around the Grayling Fingers that are like that, and on the Mansalona Plain, and this will be important in just a second. And then as you go toward Petoskey, you get a little bit finer textured soils, and that prevents the recharge because more of it flows overland, or it's held in the soil so that the plants can evaporate it and transpire it more effectively. So then we said, all right, well, let's take our 2000 scenario, or our 2001 land cover, and let's look at our pre-development scenario, and let's just take the difference, and this is the difference. Never mind trying to interpret what this fairly noisy thing is. And let's do the same thing with our deforestation. And the result of it was that compared to current day, pre-settlement had about 7.3% less recharge than we see today. So since almost all of the groundwater recharge in the Jordan River actually goes into, actually this is not just for the Jordan River, this is for the entire domain. So 7.3% less water over this region is going into the streams and discharging in the pre-settlement. So the flows during pre-settlement, assuming climate was the same, which we don't actually think it was exactly, but we don't have good data on up here, the Jordan River flow would have been somewhat less. But then, when you deforest, what happens is that compared to pre-settlement, you look at 19% more recharge, so a 20% increase. Okay, so if we go from our current, say 154 is our base level our base and most of the time level at Webster, we would look at going from that to something like 187 or 188. So it would be a very significant increase because that 187 or 188 exceeds typical spring high flows. And compared to current day, that's about 10.5% higher than we see in current day. So it's likely that right after deforestation, assuming climate was all the same, there was significantly more water actually running through the Jordan River. And if we had a better constraint on the climate, then we could confidently say this was different. But unfortunately we don't. The record keeping at the time really is not adequate for us to be able to conduct these types of simulations. But we can infer a lot based on the change in land use alone. And the last point I think before the break is that let's just focus a little bit on the Jordan River. And I've mentioned the term the ground watershed before. So what we did was we asked the model, we said, well, if you dropped a particle and at every point in our groundwater model, where does it end up? And let's just collect the entire area that goes to the Jordan River. It's the same concept as you have for a surface watershed, right? Except it's the water table that you're looking at. And so that's what we did for the Jordan River for its ground watershed. And this is a snapshot in time. This is the ground watershed from August of 2009. And the ground watershed is something that's fluid and dynamic as the water table changes. This outline, this boundary here is the ground watershed, whereas this solid, more detailed outline is the surface watershed. Key features, the ground watershed is actually 69% larger than the surface watershed. So this ground watershed drains a significant portion of the Mansalona Plain, and this provides, which is located at a higher elevation, this is what provides the rock steady flows for the Jordan River. So not only do you have very permeable soils, which a lot of places around here do, a lot of rivers, but you also have this giant groundwater shed, which is not being drained by any surface water feature. There's no surface flows up here at all. So all of the water that doesn't get evaporated just goes down into the groundwater and provides this steady source of recharge to the Jordan River the whole year long. Okay? This area provides 50% of the annual flow to the Jordan River. So if you think about management from a surface watershed perspective, you are only capturing half of the story of what's happening in your system. So this place that provides 50% of the recharge is fairly important. And there's some interesting activities that go on here that are using the water of the Jordan River, and they're using it in a specific way that is affecting the Jordan River in its current state, and will affect it going forward as you think about how to maintain the system as it is. And I'll just give you a little taste of that. Let's look at the land use map. You can see that there's some agriculture scattered throughout. Okay, there's a lot of sort of hay and field crops and some row crops. But up here, there's a big belt along the highway of potato farming. And potato farming works really great in coarse soils, provided that you can control the moisture in those potatoes. Okay? There's really critical periods in the development of the potato and in the formation of the tuber itself where you have to keep the moisture between 70 and 75% of saturation. Okay? Saturation meaning you filled up all the pore space in the soil. And that's hard to do in a fine textured soil because just a little bit of rain and that thing will saturate and run overland. So you want a coarse soil so it never really gets above 75, but it can get below 70 pretty easily. So what you need to do is you need to irrigate it. And so almost 100% of the potato farms in Michigan are irrigated, and the Jordan River, or the Mansalona Plain, which is in the Jordan River groundwatershed, is no exception. And we'll talk about that in a bit. And I think that's it. Okay. So I'm going to get to the fun part here. I've been having fun up till now. This is the part where I've kind of been doing this so far, but I'm going to make the story a little bit more explicit and tell you what we really think after years of studying this system, what we really think is going on. And when you ask the question, well, where's the sand coming from, you're actually asking three different questions. And those three are all interesting, and they all suggest that the neat thing is it's not one monolithic answer. And so that suggests that maybe there's a lot of different ways of going about tackling this problem, or the set of problems. And also that maybe the work that we've done here is something that folks from other watersheds or other parts of the state might say, well, hey, I've got this piece, you know. Maybe I could use some of the approach or the tools or the findings to help understand my problem. Maybe a little bit better than if the Jordan River, because it's so unique and whatever, had just this one problem. So anyway, so I'm going to start in the lower Jordan. And as I mentioned, by lower Jordan, I really mean up until, and I think I haven't actually shown, I showed one picture of the Jordan River itself, but I'll show more later. The mouth of the Jordan up until where it actually takes a sharp turn to the north, west-northwest, or east-northeast. So the navigable section up to the confluence with the Green River. This is annual lake levels on Lake Michigan. And I apologize that this is in meters. Just remember that about 3 feet to a meter, more or less. So what we have is, starting in about 1860, the lake level was fairly high, about 177 meters. After that, it declined to a fairly steady point for quite a while at 176.4. So it dropped about 2.5, or about 2 feet. It hit a low point in the 30s. Went back up in the 40s through the 50s and early 60s, went back down in the 60s, came back up for 30 years, and now is back down again. And this actually is interesting because the 60s, and I'll explain this, I don't want to get ahead of myself. So this is the sequence. We have maybe 20 to 30 years of a relatively high lake stand. And then it goes down, and it stays down for a while, and then actually it can change really rapidly. I mean, if you look from 1962, the average in 1960, well, it's probably actually 64. The average from here to the 2 years later or 3 years later went a full meter, so 3 feet. I mean, 3 feet can be a whole lot of shoreline. I mean, you imagine it like in Traverse, what 3 feet of change means, it's an exposed quarter-mile of shoreline, and it did that in just a couple of years. So the Lake Michigan and Lake Huron, despite their immense size, actually have a whole lot of variability compared to what we think the pre-development Lake Charlevoix did. And that the current levels, while historically not lowest, have stayed low for the longest period of time. And this decline started in about 1996. So that's an important thing to remember. So is the stream responding to lowered lake levels? So we're talking about stream equilibrium. And I want to introduce the concept of a nick point. So if this is a stable stream profile, and I'll explain this graph a little bit, this axis here is the distance along the stream channel. So this is the river mouth, and here's the lake that it flows out into, and this is the elevation. So going from the river mouth at Lake Charlevoix, for instance, you get this darker blue line. That's a stable stream profile, longitudinal profile in elevation. But if you lower that base level, say by dredging the outlet of Lake Charlevoix and dropping it 4 feet, or you go from 1996 to 2000, where you dropped a similar 3.5 feet, what happens is this is the new base level of the river, and suddenly it says, whoa, I'm out of equilibrium. I need to accommodate myself to this new lowered reality. And so what happens is you get very rapid erosion happening at the location of the outlet. That erosion forms what's called a nick point. And the nick point is maybe more of a hypothetical idea rather than an actual one, because it's kind of a smooth transition. It all depends on the scale. If you squint enough, it looks like a point. And that nick point migrates upstream over time. As it migrates, as it goes upstream, the rate of migration slows because you don't have this sharp profile that leads to an increased velocity and increased capacity to erode the bed. Nevertheless, the river has to, if the outlet drops 2 feet, the river has to drop 2 feet, more or less. And so this is a really important story for the lower Jordan River and for the outlet, particularly the last about 1.5 miles of the lower Jordan River. And I'll explain that, I think, in 2 slides. So what we tried to do is we tried to understand, well, what does the topography look like? And we've done this 3 times. We took a canoe, and we took a high-resolution GPS instrument, and we floated with it to try and get GPS values. The trouble is the gorgeous Jordan River Valley itself, with all of its beautiful trees and its wonderful deciduous coniferous swamp cedars that even after leaf off in November, and it's cold to float it in November if you haven't, they prevent receiving satellite signals from low on the horizon. And if you want to know where you are in elevation, you need to get those ones that are low on the horizon, because the ones up here, it all kind of looks the same if you're trying to go up and down. So we never really got great data along the entire channel, and I'll show you in a second. This is a picture of myself and Dr. Martin floating down the stream. This is our ADCP. We brought this boat with us last time. I just love this instrument. What it does is you put it on a boat. This instrument is this thing in white here, and every second it collects from here all the way down to the bottom. It collects the velocity, the stream speed of the stream every few centimeters. So you get this whole bunch of pictures every second, and as I move that along the stream, along a cross-section of the stream, then I can build up a picture of the flow through the channel, and it tells me exactly where all the water is flowing through the channel at a given time. Or if I tow it behind my boat, then I can find out all kinds of cool things, like where are all the pools, where the riffles and runs, and if I attach a GPS instrument on it, then we can find out what the elevation is along the whole profile, and that's what I had in mind. Didn't quite work out exactly that way. But it's like $40,000 worth of equipment, and it does some really neat things.
So when you float that, though, do you have to try to take 3 or 4 different runs?
Well, I had a strategy that I tried to stay in the river Thalweg, which is its deepest portion, which is beyond my skills. So I did my best. And I've done it 3 times now. So over those 3 times, I think, and I've got to actually combine them in a careful way, but I think I'm finally confident that I've captured all of the Thalweg portions, except I don't, I don't try and stay in those. I'm not strong enough for that. So here's our data, and this is a messy plot, and I left it messy on purpose, because in blue we have points of GPS data that these blue triangles here. We collected those in 2009. In this squares, these lighter blue squares right here, we collected those in 2010. And in 2011, with these green triangles, we collected these. We also had a second instrument, our GPS, on our ADCP boat, and that's these pluses, and those are particularly bad. So 4 tries to get this continuous longitudinal elevation profile, and we haven't succeeded. But what did work is every stop we made, so we made about 24 stops here between, probably actually this is Yeah, so there was a stop at Graves, and I'm not actually showing it, but then there's, this is probably Old State. So from Old State down, we made about 24 stops where we sat with the GPS instrument and just recorded in a stable position for 60 or more seconds, and that enabled us to get a good elevation profile along the channel. And what we see is we don't really see any nick points. So nothing that matches that conceptual picture I had, at least not in this scale. I mean, we're talking about here 20 feet and we dropped 2 feet. So maybe that nick point is just below the resolution of what we have. So we don't have anything where we can say, okay, this is where the erosion or the scour, the bed scour of the channel is taking place, or where it's at its most intense. But I did a little calculation. So, and this is a little bit by way of apology that we don't have our sediment model working quite yet. And that's to say, okay, if I just start at the Deer Creek confluence and I go 1.5 miles or approximately downstream to the mouth, what does that actually look like, and how does it behave? If you've floated the section, you know that at times you have to actually get out and just walk your boat across the sand. And, well, it behaves like one giant sand trap, actually, 1.5 mile long sand trap. And so if that lake level is a couple feet higher and your river builds up by a couple feet, it'll accumulate about 2 feet of sediment. So on average, that channel is 90 feet wide for 1.5 river miles. And if you drop the lake level by 2 feet, what you get is 50,000 cubic yards of sediment that now suddenly have to move out, because you've got to go down 2 feet, you've got to get that 50,000 cubic yards out somewhere, and I'm going to put it in the first place I can drop it, and that happens to be the East Jordan Harbor. So in 2009, the city of East Jordan, along with MDEQ, spent $90,000 dredging 50,000 cubic yards of sediment out of their harbor. So if you want to know where the sediment in the harbor is coming from and when it's coming, well, every time you have a high lake stand that drops to a low lake stand, you can expect in about 10 years you're going to get about 50,000 cubic yards of sediment. I mean, that's just the way the system behaves. Yeah, so what I did was I took all of their measurements back to, I think the oldest I got were 27 years ago, so 1980, maybe 1982. And I said, I'm just going to take the stage of the river at that point versus its discharge, and I'm just going to color code that through time. And what you see on this here is you see that there's, if you fit a curve through that, you've got a good stable curve up to about the light green. So we go down to the light green and we have about 15 years ago. So up until about 15 years ago, 1996, the Webster gauge site was behaving relatively predictably. There weren't really big shifts required in the rating curve by the USGS, and it was stable. And it had been stable for at least a 10-year period prior. Then, within a space of this light green to light blue, so we go from light green to light blue, within a space of about 5 years, this has shifted to a very different system, very different. I mean, it's 0.3 feet the system has downcut. So at Webster, there's been 0.3 feet of downcutting, and it took about 5 years for that to happen. It was triggered in 1996, which was the same time the base level of the system went down. And we know that also over this time, flows have not increased. So this is not something that's responding to a sudden new, erosive capacity of the river. This is simply that the river was flowing along, and then the bottom got dropped out, and it said, I have to flow down. I have to erode down to my new base level. And so it took about 5 years for that to propagate up to Webster, which is about, I think, 3 miles upstream, maybe 4 miles upstream. And then it took several years after that well, actually, it only took a few years for the signal to propagate. It took several years after that for it to approach what is a new, but see, it's still not there, because the light blues and the most recent points are still from there. So Webster is actively eroding. And I've got another thing I want to say about that. So I can look at this another way. So I can say, okay, well, let me take all those measurements, and they give me channel width, channel average velocity, and channel area, and I'll plot those over time. So what I found through that is that really there's no relationship of any kind between channel width and time. So the river is not changing its width. It's got the same banks, and this is the story that I'm telling about how this is a vegetatively armored bank. Okay, you've got woody vegetation that's been stable for a long time, and it's holding these banks in with its roots. On the other hand, the area has been decreasing substantially. So, okay, if you have the same channel with the same width channel, and the area is decreasing, but you have to move the same amount of water through more or less, because there's no trend in discharge over this time, you have to do it by increasing the speed of your water. And that's what's happened. The average velocity of the water has increased. And so according to Manning's equation, it's a basic way of looking at stream flow. We know that what's happening here is that in addition to downcutting, because we've seen the downcutting in the stage-discharge relationship, we have that the local slope is increasing. And that's exactly what would happen as this Nick point moves past your system, is that the local slope increases. So it takes something on the order of 10 to 15 years for this really to be fully felt over this. So it's interesting because this is something that we see in the geomorphology textbooks, but here we have a temporal example through an experiment we could never conduct, which is to lower the base level on an entire river. Or we have conducted, I suppose, we've raised the base level and lowered it with reservoirs, but with a river system the size of the Great Lakes. So I'm going to talk a couple of slides here about our hydraulic modeling. Travis is built in a tool called HEC-RAS, which was developed by the Army Corps of Engineers. He's built a hydraulic model that extends from Graves Crossing all the way down to the river mouth. And at each one of these little red lines, there's a specified cross-section of the channel that looks like this. These are elevations. I believe we measured this section. Like we took a survey instrument out with someone holding a prism, and we shot it with the laser instrument, and we measured this profile of the floodplain. Okay, this is it's not readily readable. That is about a meter. So this is an exaggerated scale. So we've got a meter from here to here, so 3 feet from the actual channel where we measured the water at to the top of the profile, and this is about 20 meters away. So this is not really a floodplain per se. It's not some flat area that the river flows out onto. So some of these, we measured at 8 points. We had our survey instrument. We measured very accurately along the floodplain. Then we also took our ADCP, which measures the bottom depth at every point, every second. And so we married those two together to build this accurate picture of the bottom along with a little bit coarser picture of the floodplain. And so he's using those along with each of these other points that we didn't measure. He's taking elevations from that digital elevation map to build channel cross-sections at all these points. And this type of model, HEC-RAS, can be used for a whole bunch of things. Most basic, you tell it your cross-sectional geometry, your input flows, and the longitudinal profile of the stream, so all the slopes, and it tells you, and then you tell it what kind of sediment you have. It says, well, what can you actually transport? Can you actually move the sand that you see moving? And the answer had better be yes. And you can alter the flows. For instance, we can feed into it, instead of the flows from current day measured at Webster, we can feed into it our simulated flows, our what was the increase from current? 10% increase or whatever from current that we saw under the deforestation scenario. And we could say, well, what would the erosive capacity been, or the sediment transport capacity been, of this segment of the river, the navigable portion, during in a deforestation scenario? So something maybe that prevailed for the first third, say, of the 20th century. And also we can look at, through a related model that you can link into this, we can actually do the experiment. We can drop the base level, and we can watch this system evolve and see what kind of times we actually see. Do we see Webster responding in a similar time frame? And that should provide us with the capacity to really look at this through time and to see this dynamic system, which is the Lake Charlevoix elevation, and watch how that propagates up. And you have changes here that happen on a year-to-year basis, and they propagate upstream, and you've got ones acting here, and maybe the system up here is still responding. So it's a very dynamic system where once we hypothesize, at least, that Lake Charlevoix was once quite stable. So we're in a different system. And until Lake Charlevoix is isolated from the oscillations of Lake Michigan, we're not going to have a stable base level on the Jordan River. So it will be, in the lower channel, a sand trap intermittently releasing 50,000 cubic yards of sediment for as long as the lake level oscillates, provided that you can't somehow shut off the sediment supply upstream. And the answer to that is we think not.
What was the answer to that again?
We think that you cannot actually shut off the sediment supply, because the sediment supply is something that probably is, in order to shut it off, you'd need to re-armor the bed. And that's something that we don't know the time scale of, but we suspect there are management solutions to achieve, and we can talk about that after lunch, but there are management solutions to achieve the fisheries goals and the habitat goals, but the sand is probably something that's here to stay.